Good afternoon, everyone. Thanks a lot for your attendance. Today, I will give a brief introduction of our project, ProFactory, improving IoT security via formalized protocol customization. This work was done when I was in Purdue, and it was a joint work with my colleagues, advisors, and professors from University of Waterloo and EPFL. First, let's take a look at the background of this project. Nowadays, IoT devices have ubiquitous connectivity, and they are almost everywhere. For the data from Statista, 4.2 billion Bluetooth devices were shipped in 2019, and forecasted by the Forbes. The market value of Zigbee will be around 4.1 billion by 2023. Therefore, IoT devices are becoming prevalent targets of cyber attacks, and more than 120 IoT-specific CVEs were newly disclosed in the past 5 years. For those vulnerabilities, performing firmware bug fixing after product shipment is quite expensive and challenging. To this end, we propose to avert such vulnerabilities upfront. Specifically, we want to formally and unambiguously model a protocol and generate a secure implementation per the protocol model. The motivation of this project is based on two key observations. First, we observe that the majority of those vulnerabilities are due to incorrect message passing. In particular, lack of sanity check, or for example, length check and value range check, and passing ambiguity, for example, diverted specification understanding across different developers. The post-mortem bug fixing and finding for those vulnerabilities is quite expensive. Now let's look at a simple example of message passing error in Linux BlueZ L2 cup implementation, where the blue lines represent the patch. The error happens when constructing a configuration response message in passing a configuration request. We can see the pointer of the buffer defined in line 4171 is finally moved in line 2999 without any boundary check, leading to buffer overflow. In the perspective of coding or programming, it is a common memory vulnerability. However, in the perspective of protocol specification, response message is underspecified, because the magic number of buffer size 64 is not clarified in any part of the L2 cup specification. The second observation is that protocol can have buggy state machines. In particular, some logic glitches, for example, message sending race. Such vulnerabilities are hard to reproduce because the state machine needs to reach the exact state to expose those bugs. This is an example of a buggy state machine in L2 cup. The two Bluetooth devices need to send an information request and reply with an information response to each other. We can observe that the two devices are actually in a message sending race at the state of the info start. It is possible that when the request from device A arrives at device B, B is still at the info start state, losing the legitimate request message. For this, the L2 cup specification just says, L2 cup implementation should responding a valid information request with information response, which cannot help much in avoiding this error. The two observations motivate our research efforts. There have been some existing work in this area. For example, for protocol modeling, there are several published papers, Everpass, PADS, Spicy, Hammer, and Nail. However, they only focus on message passers, but do not support anything about state machines. Also, except as Everpass, the security of generated passes are not guaranteed. For protocol verification, unfortunately, the majority of them just focus on cryptographic correctness, and they overlook the fundamental state transition security issues in general state machines. To this end, we want to propose ProFactory, which defines a unified DSL to describe both message format and state machines, and generates secure protocol implementations. This is a ProFactory system architecture. First, developers model a protocol in our DSL, including message formats and state machines. Then ProFactory will translate the protocol model to a constraint model, performing symbolic model checking. If the model passes the checking, ProFactory will generate a kernel-oriented protocol implementation in C language according to the protocol model. Meanwhile, a set of hard-coded platform-dependent interfaces will be integrated into the implementation. Those interfaces are system and hardware specific. For example, Bluetooth device connecting and delayed kernel work scheduling. and we must respect them. Finally, the implementation will go through the verification of memory accessibility and concurrency. If the verification passes, the implementation is considered secure to deploy. In protocol modeling DSL, for message format, we define 6 abstract types: fixed sized field, variable sized field, message header, protocol parameter list, and a message. The recursive message type defines a tree-structured message group that is identified by the message header. The right side is a semantic folder. The big F represents how we parse, compose, and fetch the message and its corresponding fields, and it is for code generation. The big P here denotes the update of the constraint model, which is for symbolic model checking. Because of time limit, details of the semantic symbols will be skipped here, and the interested audience may refer to our paper. For protocol multiplexing, we define 2 socket types, channel and connection, that contain a list of protocol parameters. Channel can multiplex the underlying connection, and the channels can be indexed by different protocol parameters. For state machine, we define the protocol state, message receive, and message send behaviors. It expresses how the message payload without any message headers is processed and how the state transition is performed based on the processing of the message content. Here we have a real-world example for the Bluetooth L2 CAP protocol. We just demonstrate that even the complex Bluetooth L2 CAP protocol can be well specified by our DSL. For all the kind of details, interested audience can refer to our paper. Next, this is a ProFactory code generation algorithm. The generation is purely type-based, and it is a recursive procedure. We partition the code generation into different blocks. Here, struct_gen for data structures, local_gen for local pointers, extract_gen for pointer references, check_gen for sanity checks and range checks, alloc_gen for buffer allocation, and so on. We generate codes for message format-related types, socket types, message parsing, message receiving, and message sending. In particular, for all the socket buffer operations, we generate the skbuff data structure, and the kernel takes over all the memory management of this data structure. So we don't need to care about any memory access violation of this data structure. For code verification, ProFactory translates the protocol model to VCC specifications to perform concurrency verification on the concurrent accesses to share the data in multiplexing. For memory safety verification, ProFactory translates the protocol model to Frama-C specifications to perform deductive verification based on the weakest precondition logic. The verification relies on per function annotation. Because VCC and Frama-C are not our main contribution, I will just show 2 short examples of the specifications. This is an example of VCC specification. It translates the mutex operations to a data container, which is locked by a data log. Whenever a shared object is accessed, the log must be claimed, and the object must be unwrapped. The ghost keyword here refers to concurrency-related auxiliary object in this proof. Next is the Frama-C specification. A function needs to be annotated with pointer validation, memory chunk separation, loop invariance, and loop variance. Those annotations highlighted in green in this figure will serve as lemmas in the deductive verification. Note that most of the annotations can be automatically emitted, but developers may still need to add a very limited amount of loop invariance and constraints to assist the proof. For symbolic model checking, we translate the protocol model to SMT lib specifications and check 6 state machine-specific properties based on 2-peer communication under semi-honest assumption. State reachability checks if there is any state that's not reachable. Transition coverage checks if there is any state transition that is impossible. Absence of transition conflict checks if any 2 transitions of one state can be satisfied at the same time. Race-free message sends checks if there is any message sending race. For example, the motivating example 2, Dialog-free message receives check if there are two peers can get stuck when they are both waiting for an incoming message. Consistent security level checks if security levels are the same across all the paths to a state. The first 5 are general state machine properties, and we want to showcase the 6th one, a security-specific property. Here is a CVE found in Bluetooth PAN implementation in both Windows and Android, where a victim's internet connection on Bluetooth can be tethered by the attacker without authentication when the attacker pretends to be a PAN user. The root cause is that PAN start can go from either transition 1 or 2 to reach the PAN ready state. However, transition 1 requires authentication security level, but transition 2 does not. It leads to a security downgrading error. The official path just deletes the transition 2, but however, we think we could just split the PAN-ready states to support both cases. In performance evaluation, we modeled and generated an implementation for several Bluetooth and Zigbee protocols, and we can see that the size of customized protocols can be much smaller. We also tested the performance of file transferring service over Bluetooth RF-COM, and our generated codes only incur 4% overhead compared to the original implementation. We collected newly disclosed Bluetooth and Zigbee vulnerabilities, and we found almost all of them can be averted if ProFactory was involved in protocol modeling. The only one that could not be averted is about crypto key cracking, which is not covered in the current ProFactory implementation. Although ProFactory can help generate secure protocol implementation, it still has several limitations. We don't have support of modeling flow control algorithm. If any DSL specification flaw is found, the security guarantee could be degraded. We don't have formal proof of semantic preservation regarding the code generation part. We don't have support of modeling cryptographic constructs, and it may require the integration of the existing tool to support this. Also, we have heavy dependence on the platform and hardware-specific interfaces. It's inevitable, but it can be mitigated by a virtualization layer. To conclude, we propose a ProFactory which offers DSL-based protocol modeling that covers both message formats and state machine, and is applicable for general IoT protocols, and it can help generate vulnerable free code, avoiding lots of no vulnerabilities. Yeah. That's all my talk today. Thank you so much.